Good morning, students. Today, in the Unit 3 Laws of Motion, we are going to see the topic Dynamics of Circular Motion. So, in the topic itself, we know that dynamics. You know the difference of statics and dynamics? Static means there is no change. Dynamics means it can change. So, the circular motion can change. So, in what aspect is change? That is, we are going to say in this. So in your previous sections, you have studied how to analyze a linear motion using the Newton's law. So now we are going to apply the Newton's law in a circular motion. What is a circular motion? You know that, okay. The movement of the particle in a circular path. So the circular motion needs the force. If it is a linear motion, with the force or without the force, it's possible. But a circular motion, the force has to be there. There is no force, no circular motion. In simple words, Newton's first law is not for circular motion. That means there is no force, circular motion does not occur in nature. So, how the circular motion changes? So, a force can change the velocity of the particle of the circular motion. So, in three different ways. How it changes, how the velocity it changes. First thing, the magnitude of the velocity can change without changing the direction. That means, if the particle falling down vertically, okay, so it goes down, but the direction is not changes. Its velocity, its magnitude is changing. Okay, the next best example for this one is bike riding on the road. So the bike is going straight, its direction is same, but the magnitude is different. So it moves with the acceleration. Okay, and the next thing, the magnitude is same, but the direction is changing. Okay, so it changes the direction, but it covers the same distance. So it's continuous means it's a uniform circular motion. And the third one, both will change. The magnitude also changes, the direction also changes. So this possibility is known as non-uniform circular motion. And the best example for this non-uniform circular motion, you all know that the swing. Swing, you know. So swing is nothing but it executes to and fro motion. So this to and fro motion, its direction and the magnitude both will change. And also the one more best example of it is simple pendulum. You know that is also to and fro motion. So that there also the change in the direction and the magnitude. Discussed about this uniform and non-uniform circular motion. So next we pass on to the next one. If a particle is in the uniform circular motion, means there must be a centripetal acceleration towards the center of the circle. If there is an acceleration, we know that there must be a force in the frames. So that force is nothing but a centripetal force. So you know the centripetal acceleration of a particle in the chapter 2 itself. In for a circular motion, what is given? A is equal to V square by R. So it acts towards the center of the circle. So according to the Newton's second law, the centripetal force is given by, that is F is equal to ma, we know that. So for this centripetal force is given as FCP is equal to MACP. That is nothing but the acceleration. We are writing the acceleration as V square by R. So instead of that we are writing V square by R. So we are getting mv square by R. So the centripetal force means center seeking force. That means it towards the center. Okay, the force is towards the center. Always it's going towards the center, at the center point. So it's a center seeking force. So in vector notations has to be given. FCP is equal to minus m omega square r cap. Okay, so that minus r is nothing but the it denotes the direction pointing. Okay, it is pointing the direction of the centripetal force. So now you see this diagram, you know the directions. Okay, so see this diagram. see the center point, okay, it's O. And what about the four forces? All the forces is towards the center. So that's why it's called as a center seeking force. Okay, centripetal force. See the velocities, it going outwards, but the force is towards the center. Okay. It should be noted that the centripetal force is not like the other forces as like gravitational force or the spring forces, because this force is always towards the center. Okay, it's a center pointing force. The origin of the centripetal force can be due to the gravitational force or the tension in the string or the frictional forces or coulombs, etc. That means any of these forces can act as a centripetal force. How it can act, that's we are going to discuss. First see this diagram. See this two diagram. First see this first diagram. A man having a string, or having a string, that is a stone is tied to a string. Okay, so the wheeling motion of a stone tied to a string, here the centripetal force on the particle is provided only by the tensional force on the string. So due to that only the centripetal force is acting here. And see the second diagram. Okay, the you see, or you see this picture in the that means this thing in the amusement parks, right? So in a circular motion in an amusement park, the centripetal force here is only provided by the tension of the iron rod. So here the centripetal force is acts as in the tension force. Okay, tension in the string or tension in the iron rods. And the second case, we will discuss that in the motion of a satellite around the Earth, the centripetal force is given by the Earth's gravitational force on the satellite. That is a Newton's second law for the satellite motion is F is equal to Earth's gravitational force. That is nothing but mv square by r. Here the r is distance of the planet from the center of the Earth. Okay. And here m is what? Mass of the satellite, and v is nothing but the speed of the satellite. And come to the third case, that is, see this diagram. This one, the car in the circular track. When the car is moving on a circular track, the centripetal force is given by the frictional force between the road and tire. So the road and the tire of the car is having some frictional force, and that frictional force acts as a centripetal force here. When the car moves on a curved track, the car experiences the centripetal force, which is provided by the frictional force between the surface of the road and the tire of the car. So between the tire of the car and the surface of the road having a frictional force, and that frictional force acts as a centripetal force here. Okay, so here we are taking again the Newton's second law for this case, that is the frictional force is nothing but mv square by r, and that mv square by r, m is the mass of the car and v is the speed of the car, and r is nothing but radius of curvature of the track. Okay, and see this one, this is given here a cleared picture. Okay, the FCP is nothing but the centripetal force, and that centripetal force is nothing but the frictional force between the surface and the tire of the car. And the fourth one, see this picture, you know that sun and the planet, it moves along an elliptical orbit, and there also a centripetal force. The planet orbit around the sun, they experiences a centripetal force towards the center of the sun. So gravitational force of the sun acts as a centripetal force on the planet. Okay, and here also we are going to apply the same second Newton law for this motion, that is the gravitational force of the sun on the planet is equal to mv square by r. Okay, so all these cases different forces or act as a centripetal force. So in the first thing, that is the wheeling motion of a stone tied on a string. So the string and the iron rope both having the tension of force, and that force is act as a centripetal force. And in the second case, the movement of the satellite around the earth, there also the gravitational force act as a centripetal force. And the third one, the car is moving on the track, and that there the frictional force is there between the surface of the road surface of the road and the tire of the car. Both will have the frictional force, and that frictional force is act as a centripetal force. And the last one, that is the planet around the planet orbit around the sun. So both, in that case also, it having the gravitational force that acts as a centripetal force. In all these cases, we are applying the Newton's second law of motion. That is, according to that, the m and v must be changing. Okay, for in the third cases, it changes as the mass of the car and the speed of the car. In the second case, it changes the mass of the satellite, and v is the speed of the satellite. Likewise, changes has to be there, but the Newton's law of motion is same for all the centripetal forces as mv square by r. So regarding with this, we'll discuss the 3.22 problem is given. See that problem, it's a very simple problem. If a stone of mass 0.25 kg tied to a string executes uniform circular motion with a speed of 2 meter per second of the radius 3 meter, what is the magnitude of the tensional force acting on the stone? So all the values are given. It's a straight substitution. M is given as 0.25 kg. So we are taking in a fraction. It's nothing but 1 by 4. And then V is given as a speed, that is 2 meter per second. And radius is also given as 3 meter. So straight substitution, right? FCP is equal to mv square by r. That is Newton's second law of motion. Equal to, in the place of m, we are going to substitute 1 by 4, and in the face of speed, we are substituting 2 meter per second, and in our place, we are substituting the 3 meters. And multiply, you will get 4 cross 4 get cancelled. So it's 1 by 3, and dividing 1 by 3, you will get 0.333 newtons.